Okay, so part three, we left part two with this question, and hopefully you have solved this. And by the way, not everybody will have the same answer because there are many ways to write different equations, parametric equations of the same line, right? How do you solve a system of equations like this? This is definitely dependent because you have three unknowns and the two equations, right? And clearly this is dependent because you know the answer is going to be line, which consists of infinitely many points, not just a unique solution. Okay, so I think I will take equation one and multiply this by -2, because we're trying to eliminate something, right? So this will give you -2x plus 4y minus 2z. Now, again, there are all kinds of ways to do this, so you didn't have to do it this way, but if you multiply equation one by -2, you have this, and then you can, let's call this 1 prime because this is just like 1. Now you can add and find the sum of these two last equations. The point that we were trying to make is, of course, these will cancel, and so 7y. And interestingly enough, I was trying to cancel just the x, but these two will also cancel. Very nice. So 7y is equal to 14. Look, we found y is equal to -2. Nice and simple, right? Now you can plug this back into one of them, okay? So let's say back into the equation one, and it'll tell you x minus 2 times -2. So this part will be plus 4 plus z minus 5 is equal to 0. What is it saying? X plus z is equal to 1. Okay, so that's what we just found out. And that's about it. Because see, I mean, there is no simple solution, one solution, right? So you can let x and z be anything you want. All we need is y is equal to -2. So you can let x be 0, okay? And then z must be 1. You can use x is equal to 1, z is 0. If you are, sort of weird, you can let x be 0.7 and z be 0.3. I guess that would work. But anyway, if your point satisfies both of these, then that would be okay. So let's use the point. Hello, yeah, 0, -2, 1. Okay, again, you may have been using different, you may have used different points. That's as well. That's fine. All right, now we need a vector that is perpendicular to both P1 and P2, and that is a vector that is parallel to the line of intersection, and that's simply this. I've written it this way. You can imagine IJK here if you have to. You shouldn't have to. Anyway, what is that? -4 minus 3, that's -7, okay? And then the next one is 2, remember, negative of 2 minus 2, that's -0. Otherwise known as 0. Last one is 1 times 3. That's 3 minus -4. That's 3 minus -4, and that's 7. That's my vector. Or, you know what? Let's just not call this n. I just found just any vector that is parallel to the line of intersection. Simply just use let n be equal to -1, 0, 1. Clearly, this is parallel, and it's much simpler to write. Okay, now I have an equation which goes through. Now, sorry, it's a line that goes through. So the line whose parametric equations are x, y, z are 0, -2, 1, plus -1, 0, 1, and then t, t, t. Well, you don't have to write all the unnecessary things here. I think you can do better. X is -t, y is -2. Notice here, by the way, y has to be -2, regardless of t. Okay, so this y value will not change on this line of intersection, which, by the way, means it is parallel to the xz plane. Not clearly understood from the problem. And then the last one, z is equal to 1 plus t. Okay, so these are the parametric equations. Again, you may have a very different equation. You may have a -70 here, but I hope that you will get y is equal to -2. This part will not change regardless of what types of equations you came up with. So if you replace this t with 70 and this t with 70, that's okay. You can still have the correct answer. Okay, so far so good. Again, make sure you apply these ideas, skills you are obtaining as you do your exercises, homework, assignments for these sections. All right, number 5. I'm going to have one more section. This is the middle of section 3. All right, number 5 is the distance, and we have just one more. Well, let's see. Is it 2 more? Number 5 and number 6, and then that would be the end of the section. Number 5 is the distance d between the point and the plane. So what does the point and the plane look like? Okay, well, let's go ahead and draw a picture of this. All right, so you have a plane. Oh, by the way, this is also very clever. Okay, now again, I can give you the answers, formulas, and many people actually do that. They just get the formula from the book and then use that formula. I have a better idea. Okay, learn where the formula comes from, because then like me, if I forget this formula after a long summer, I can just recreate this formula, right? And that is what mathematics is all about. Not about recreating, but thinking. Okay, thinking about where the formula came from, and if necessary, just construct it again so that you can come up with the formula, and that would make you a good math student because you will have deeper understanding of this. Okay, so what we are given is this. Distance between D, I don't know, that's what you're looking for. A given is the plane P, here's a plane, right? And the point Q, that's not on the plane. And we are trying to find the distance between Q and this plane, this point P, Q, all right? How do you find this? Because if you pick a random point P on this plane, clearly the length PQ is not what you're looking for. You know what I mean by the distance D between this point Q and the plane, right? What you have to do is to draw a perpendicular, which is a perpendicular line segment from Q to the plane, and then you find the distance, okay? So that is what we're looking for. How do you find the distance D between Q and the end of this perpendicular that's drawn from Q straight down to the plane? It looks like a hard question, okay? But again, I want you to see what you're about to see in the next 10 minutes or so and see how clever this is. This is a beautiful construction. Let me just come up in your face here. See, yeah, this is an excellent expression, and you need to know how elegant this construction is. You ready for it? All right, so here we go. Let's go back. Okay, so how do I do this? Here's a clever method, all right? And you wouldn't believe it because it sounds almost too good to be true. A clever method here is to do this. Let's pick any random point P. I'm going to pick any easy point P on the plane. You are given the equation of the plane, just find like 0, 0 something or something 0, 0. Find an easiest point on the plane, and schematically this is what it looks like. And then you find, oh, that's not what I was going to do. Find PQ. So I'm going to find the vector PQ that will connect from P to Q. Then use trigonometry to find D, okay? Now, what in the world am I talking about? So here's my line from P to the base point of the projection. And somehow this is going to tell us how to find the length from the distance from Q to the plane, which is denoted with D. All right, so the angle here is, of course, we can call it theta. Right? How do you find D? Well, the D, if you look at it, the length D is, of course, the hypotenuse, which is PQ, and the length of PQ is the hypotenuse, the length of the hypotenuse of this right triangle, times what? Well, the distance D is, of course, the side length of the opposite. So this is sine of theta. Oops, sorry. I didn't mean to do that. Okay, so let me go ahead and erase this. Sorry about that. I don't want to have that angle, because the thing is, you don't know this line that I drew with the pink, right? What you are given. Sorry about that. Let me go back and fix this. All right, what you are given is this line. Now, how do, the vector? How do you know this vector exists and it's easy to find? Well, because you will be given the equation of this plane, right? So if you're given the equation of the plane, it's easy to find that normal vector because it's basically ABC, the coefficients for x, y, and z, right? And so look at this picture here. You can find the angle between the given vector n and the vector you found, which is PQ. Now that's theta, okay? But you notice here, you have two parallel lines. N is parallel to this perpendicular, Q to this point here. So by what we call the alternate interior angles, do you remember that? This is also theta. Okay, if you don't remember this, that's okay. But the point is, these two angles have the same measurement, all right? So the angle between n and the vector PQ is also the same as this interior angle. Now, D, the distance happens to be the cosine of the angle, right? Times PQ. So this is not the sine, but it's the cosine of this angle here. Okay, that's the distance that we want. And if you don't understand this, you can pause this, look at this, stare at this picture for a few minutes. I think you will understand that, right? Because D is the length of the adjacent, which is the hypotenuse length times the cosine of Q, cosine of theta. All right, how else can I figure this out? Can I write this? You have the norm of PQ times the cosine of theta. That itself is not very attractive, but as soon as you put another vector here and the norm of another vector, of course you can't just do that on the top, you have to do it on the top and the bottom. Suddenly it looks very pretty. Okay, why the addition of this mass becomes a pretty thing? Well, because now the top is just the dot product. You know, who came up with this wonderful idea? I don't know, but it is beautiful, right? Oh, by the way, the cosine, you know, the distance d is positive, so you want to have the absolute value here because the angle theta could be actually acute. You know, if you'd had the normal vector this way, the angle between n and PQ would be a negative, or the cosine of the angle would be negative. But again, the cosine of an angle is negative of the cosine of the supplementary angle. So all you have to do is to take the absolute value. So you would have to do that. And so the numerator will be the absolute value of the dot product, and the denominator is simply n. This is it. Okay, you see how simple this equation is? This is how you find the distance between the point Q and the plane, you know, on which Q does not belong. All right, so this, by the way, is an equation that's slightly different from the book. I prefer this one because this is first elegant. You know, I am biased. I like beautiful things, and you should too. But the thing is, there are other formulas, but this is probably the best way to figure out the distance between the point and the plane. All right, so let's look at an example. Find the distance, and by the way, again, this takes practice. All right, so after like 2 or 3 exercises, you'll be good at it. After 200 or 300 exercises, you'll be really good at it. Find the distance between 2, 6, -1. You don't have to draw this, okay? And this plane, okay? So again, imagine here's a plane, and it doesn't matter what orientation. This point is 2, 6, -1, okay? And then I'm going to pick Q. Now remember, n in this case is what? Perpendicular, okay? That n is 3, -1, 1. Easy. Just look at the coefficients, and you can figure out this n. Okay, we will use that in just a moment, as you can see here. Right? Pick a point P, any point on this plane. Now, what would be a great point on this plane? Something that's really easy to see. You know, I wouldn't let x be 5 and y be 32.3 if I were you, right? I think we can all see 0, 0, 10 is on this plane because this satisfies this equation. right? If x is 0, y is 0, z is 10, then this expression is equal to 10. P is definitely a point on the plane. All right, so PQ is this vector. Now you do a subtraction, so that's 2, 6, and negative 1 minus 10 is negative 11. Okay, so that's my PQ. All right, so now the distance D, remember, is N dot PQ. And in case it's negative, you take the absolute value, and then the norm of Q. The norm of Q is very easy to calculate. That would be the square root of 3 squared plus 1 squared plus 1 squared. Technically, it's negative 1 squared, but who cares, right? All right, so what is the dot product of this and this? Well, dot product is such a nice thing, right? So it's 3 times 2 minus 1 times 6 minus 11 times 1. So the top is basically the negative 11, absolute value is 11. The denominator is 9 plus 1 plus 1, that's the square root of 11. Well, I told you don't have to rationalize the denominator, and you don't, okay? But hopefully you can see this is easily written as the square root of 11, which is the distance between Q and the plane. Now, it's really hard to find the equation of, here's a plane, and here's a point. How far is this? How far is this point from the plane? It's not so easy to even try to figure this out geometrically. There's a way to do this in calculus by minimizing a differentiable function. But you don't need to know any of that stuff, okay? This equation here tells you exactly how to find the distance between the point and the plane. Beautiful expression, right? And so I hope you learned that. And maybe you can explain this to somebody else. And after you explain that to like 3 people, you'll have this done. Okay. So similar question. Before we go to, this was point 5, right? Before we go to point 6, which is the last point of this section, what happens if you have 2 non-intersecting planes, basically 2 parallel planes? Okay. Can you think of a way to figure out how far apart the parallel planes are? Hint, just look at the first part. Yeah, I mean, you can just pick a point Q here in the first plane, pick a point P in the second plane, and you do the same thing because the distance between Q and this first plane is, exactly what you want, right? So the answer is just pick Q on one plane and P on the other. And you use the technique that we just found, okay? And I'll show you, and this is a little deceptive, and some students just find this to be a little confusing. Okay, so I have 2 planes. X minus y plus z is equal to 3. Another plane, x minus y plus z is equal to 7. How far apart are they? The answer, some people say, oh, that's obviously 4. Well, because, it's 3 and 7. Okay, but forget, all right, so here's what's happening. These planes, we don't know exactly how they're oriented, right? If you measure it this way, the distance is actually 7 and 3, and this length here is 4. Okay, but that's not the distance between the 2 planes, right? In order to find the distance between the 2 planes, I need to find something perpendicular. We're trying to minimize the distance between the 2 planes. And this has to be perpendicular to both of these planes. So how do I do that? Again, it seems like a hard geometric problem, except that now we have this picture and we know how this works. And you may want to draw a picture of this too. I have this equation 1, plane 1, plane 2. By the way, n from both of these is 1, negative 1, 1, right? So here's my point Q. Let's pick the point P, and you have this n. And what I'm looking for is this distance D. I can find the point, or I can find the equation PQ. Except I haven't got the point PQ or P or Q yet. All right, so let's pick a point. Let Q be a point on this first equation. What would be a good point? How about 0, 0, 3? Now you can use 3, 0, 0, or 0, negative 3, 0, I guess, but 0, 0, 3 is a pretty easy thing to do. Okay, how about from this? Okay, P, oh, that's not a vector. P comes from the second equation. And how about the SPI? 007. Is this on the plane? Yeah, because 007 does satisfy the second equation, right? So 007 and 003. What's going to happen here? Okay, well, PQ is 0, 0, negative 4. And I already told you N is 1, negative 1, 1, right? All right, the distance D is PQ dot N divided by the norm of N. Do you have to memorize this? Yeah, it helps to memorize this for now. You know, you can easily forget this and that's fine. But I think if you understand this process here, you will be able to construct it. That's what I do every semester before I teach this class. Maybe I just deliberately forget this so I can do this, you know, this process again and again and again. I won't have absolute value in case, you know, this is negative. Okay, what's the dot product? 0, 0, negative 4. So the top is negative 4. The absolute value is, of course, 4. And the numerator, the denominator is 1 square plus 1 square plus 1 square. That sounds like 3 to me. So the answer is 4 over negative 3. And that is the distance between those two, those two planes. Not 4, okay, but 4 over the square root of 3. Okay, I was actually going to pause before giving you the answer, but now that I have gone over this, I'm going to stop this segment or part, and then the part 4 will start on the page 5, which is number 6, the last point of this section, which is the distance D between a point and this time a line. Okay, so you have a point P and the line Q. How do you find this distance? That is what's coming up. All right, so I'll see you in just a bit. Go to the part 4 of this recording when you are ready.